Designing a better battery for next generation devices often come with challenges which conventional components cannot keep up with. Here in our project at Monash University, we have been working on finding new lithium fluoroborate salts for their use in energy storage devices, and we have recently published this. In this video, we explain how we prepare new anion systems and test their application in next-generation lithium batteries under practical conditions. So what is the motivation behind choosing these new fluoroborate salts? We have found that these fluoroborate salts are not only influential for lithium, but also for sodium and magnesium systems. In the next part, we have Dr. Binayak Roy demonstrating up close on how we synthesize these new salts and test their battery applications.
Hi, I'm Binayak Roy, and today let's have a look at how we are making these novel lithium salts and electrolytes for next generation batteries. The journey of our novel materials starts from their synthesis. Precursor chemical materials are often moisture sensitive, so they needed to be treated under extreme care. Once synthesized, these materials are transferred into an argon-filled cloth box to prepare electrolytes and test their performance in coin cell batteries. We attempt to keep this condition under which these batteries are tested as realistic as possible so that we can predict the behavior of these novel materials in their practical application. In our early tests, we have seen our material to perform better than the conventional ones in a coin cell made with next-generation lithium battery materials. Traditional salts are known to corrode aluminium current collector at high potential, which can be observed as the formation of corrosion pits. When treated under similar conditions, our fluoroborate salts does not show such behavior. Most importantly, our material have shown stability under atmosphere, and this comes as a major advantage over conventional batteries, which are very sensitive towards atmosphere and therefore requires them to be made under argon and completely sealed before bringing them out to atmosphere. In our battery cycling experiments, we have seen that this exposure of salt has minimum effect on their cycling capabilities even after 1,000 cycles. We are still exploring new properties of these materials, but we are certain that these materials can be used in making atmosphere-friendly batteries in future with higher safety. Another important part of our research is characterization techniques, which helps us to better understand the behavior of these materials in a battery. For the next part, I'd like to hand over to my colleague, Dr. Pavel Cherkonov, who is an expert on such characterization techniques, to explain this a bit more.
Understanding the battery chemistry behavior is very important. Monash has a suite of highly specialized equipment for characterization of energy storage materials. One of them is X-ray photoelectron spectroscopy, known as XPS. Samples are treated under argon atmosphere with no exposure to air at any stage for an accurate chemical analysis.
Work there from Pavel on the characterization of these materials. This research forms part of the work of an Australian Research Council-funded Industry Transformation Training Centre called Store Energy. The aim of Store Energy is to collaborate with local industry in the training of young researchers in advanced technologies. In this project, we are collaborating with local company Calix Limited. Calix is a New South Wales and Victorian-based industry that produces advanced battery materials. Here at Monash, we combine these with our novel electrolytes with the goal of developing high-voltage lithium-based batteries.
These materials have major prospects in the automotive industry and the energy storage sector, as well as the Australian economy at a larger scale. We hope that you have enjoyed the demonstration of our research facilities and the work made by our colleagues here at Monash University.